Welcome to today's session. My name is Kevin. I will be getting us started today. A recorded version of this webinar is going to be available for you guys on our website, our YouTube page, and linked in our post-webinar email as well. I want to take a quick moment to go over some housekeeping items. In the top right of your screen, there's a questions tab. We'd love to hear from you. So if there's, I know some of you have already submitted some pre-submitted some questions for us today. But if you have any additional, that's a good place to put them. And it's also a good place to ask for if you have any technical issues. I'll be monitoring that closely. And lastly, there's a settings icon where you can control your audio and visual settings. For those of you that are just joining us, welcome. Thanks for being here. I'd like to start introducing some of our hosts and panelists we have here today. From Intertech, we have our Chief Operating Officer, Tim Wright, our Quality Assurance Manager, Justin Job, our Director of Product Management, Jeremy Vonderhaar, and again, my name is Kevin. I am the Events and Marketing Strategist here at Intertech. Finally, our presenter, John Siegenthaler, is here with us. He's the Principal Engineer for Appropriate Designs. He's joining us today to talk about small-scale chilled water cooling. But before we get there, I'll hand things over to Tim Wright, who will give us a brief introduction. Tim, the floor is yours.
All right. Hello, everybody. It's exciting to bring this webinar series to all of you. It'll be cool to be able to figure out where this reached. So just a real quick introduction. We can't thank you enough for joining us, but this whole idea of modern hydronics and heat pumps, this is going to be a series. So my encouragement to you today is obviously enjoy this first one, engage with us, and then you will find that there's going to be multiple other segments that are going to be coming your way from John and from Justin. So we're super excited about bringing this series to you. What we're trying to do here is obviously break down some walls and just demystify what hydronics can actually do for you. And I think to many of you, we have witnessed hydronics just can't get me where I want to go. And I truly believe by the time John and Justin are done with you, you will have a pathway. You'll have a new opportunity to be able to see how modern hydronics and heat pumps are the way to go. So I just want to do a little thank you, a little shout out to all the media publications that also help push this out. Very, very much appreciated on behalf of Enertech. But if you're a utility and joining us today, we want you to be able to understand how you can head toward decarbonization, how you can really help your customers. If you're an engineer, we want you to be able to see that there's actually applications that you've probably heard aren't possible or can't be done. If you're in the HVAC industry, to me, this is all about what can you do when you pull up to that job site, whether it's a new construction, whether it's an existing home or a multifamily, light commercial. I truly believe that your eyes will be opened and opportunities, will be granted to you. So this series is really for you. And I just trust that you will engage with us and ask incredible questions. Please bring those. We're going to do some fun polls that Jeremy and team are going to help with along the way. But just real quick about Enertech. Enertech began in 1996 as what I would classify as a boutique distributor. And from that point on, we really believe that geothermal, ground source heat pumps, and eventually having an air product was the way to go. So that is obviously forced air systems and as well as hydronic systems. So that is what we do. And it's all built here in the United States of America. We also headed toward manufacturing in 2007. So a distribution from 96 all the way to 2007. We just knew that we needed to take that next step to really help our own destiny and to guide our own pathway and what we could bring. All the way through to 2020 is when we started manufacturing the air to water heat pump and started perfecting it. And I believe that you'll be very impressed with where we are today. And obviously, Justin and John will be able to share with you where we're going. So we really want to help lead this industry. It's a fun topic that we're going to jump in today. And I'd really love to be able, if I may, just give an opportunity here to thank John and thank Justin for the time that they've invested into this already. But Justin's been a part of Enertech since 2017, actually. and he's held many different positions inside of Enertech. But where we honestly have needed Justin the most is to be able to help really with the advancements of variable speed technology. So Justin's been all over Canada and United States, seeing many, many different applications, bringing that information back to our engineering team and our research and development team, and being able to really make sure that, hey, what is needed in the field, let's make sure that we can build that. Let's make sure that that's what the market is truly ready for. So we've recently just transitioned Justin into a quality assurance. We truly believe that Justin being able to spend time in between Mitchell, where we manufacture our product, that's Mitchell, South Dakota, and also Greenville, Illinois. We have two manufacturing facilities we're very, very proud of. Again, both of them built, everything built right here in the United States of America. So with that, Justin, happy to have you on board. John, thank you for bringing this to us. Take it away, guys.
Well, thanks, Tim. I'm excited as well to be here. It's inevitable that hydronics and heat pumps, those two market paths, are going to cross. It's opened up opportunities that we've never had in the past, specifically cooling, small scale cooling, residential like commercial buildings. So I'm excited to go through the first of our webinar series and then to also look forward to doing more in the future. So let's talk about small scale cooling. Now, many of you know that hydronic-based cooling has been used in the commercial industrial sector for decades, dating back really into the 1960s. So why is it applicable today on a smaller scale? Well, there's quite a few reasons. Hydronics in general is thought of in North America as a heating technology. And when it's properly executed through design, installation, maintenance, and so forth, it can produce unsurpassed comfort. It's had a long reputation for that, but still it is largely thought of as a heating technology. And you can see here that has been what I'll call an Achilles heel for hydronics for quite a few decades. Oftentimes, as I've dealt with customers or potential clients, oftentimes they'll get quite excited about what we can do with hydronic heating, be it radiant floor heating or systems that bring that together with domestic water heating, snow melting, and so forth, the versatility of hydronic heating. And then the question comes up, well, what do I do about cooling? And obviously boilers don't provide that cooling. So it's been a gap in our market, but with both geothermal water to water heat pumps as well as air to water heat pumps, when you buy one of these heat pumps, you're buying not only a heating machine, but you're also buying a chiller. They're all equipped with reversing valves. So very simple electrical connection can switch them from a heating device to a cooling device. And, in looking at the market, one of the interesting things, and I'd encourage you to look at this website here from probuilder.com. They do a lot of market research on residential construction. What are the trends and so forth? And Generation Z, these are young people starting their careers or perhaps a few years into their careers, getting to a position where they're interested in potentially investing in a home. And one of the surveys that ProBuilder ran showed that 80% of these Gen Z potential home buyers would not consider buying a home without central cooling. And if we think about it today, we have cooling in our workplace. In general, we have cooling in our cars. We even have cooling in our tractors. So we're used to it. And as a culture, as a society, we've become used to cooling. And even though I grew up in a house without cooling today, especially with warmer climates than we've had in the past, cooling is very much a sought after technology or a sought after benefit in construction. So putting this together with where state, provincial electrification plans are going, federal level plans, things like net zero construction, we're really setting up a fantastic market opportunity to bring hydronics and heat pumps together, offer cooling as well as space heating, domestic water heating, and other technologies. We can integrate it all into one system. So I want to start off with what's a hydronic heat pump. I mean, everybody has heard about heat pumps, and they come in what I call different flavors. The most common being air-to-air heat pumps. Today we see a lot of ductless mini-split heat pumps, but largely it's been air source and air side delivery. Excuse me. So a hydronic heat pump is water side delivery. And here's an example. Here's an Enertech air to water heat pump and what's called the Advantage system. Here's another product from Enertech. This is a water to water variable speed heat pump. So both of these heat pumps, even though their sources are different, air source heat pump versus water source heat pump, the delivery method is virtually identical. And so any heat pump that delivers heated water, chilled water to a hydronic distribution system would be considered a hydronic heat pump. And the important point I want you to focus on today, that most of the balance of system design concepts, and I've listed a few of them down here, most of these apply equally to whether it's an air to water heat pump or a geothermal water to water heat pump. We have to respect the operating limitations of these machines, both in terms of temperatures and flow rates. We have to do the fundamental hydronics right. For example, providing hydraulic separation of multiple circulators in the system. So even though we're going to focus a bit more today on the air to water heat pump, the concepts that we talk about could be equally applied to the water to water geothermal heat pump. So what's some of the reasons that chilled water is beneficial? Well, one of the arguments that's always been true, whether it's heating or cooling, water fundamentally is about 3,500 times better at absorbing heat on a volume basis compared to air. It's just the cards we've been dealt with. It deals with the specific heat of water, and it also deals with the density. Both of those, we don't really have control over those, but when we roll those together, we find that the heat conveyance capacity of water is tremendous compared to air. So here's a comparison where I just took a nominal 1 ton or 12,000 BTUs per hour and sized up a hydronic delivery method. We could deliver that with a 1/2-inch tube with a 20-degree temperature drop in the case of heating. If we were going to do the same distribution using air and we wanted to use round ducts, we would need a 9-inch round duct or a 7x10 rectangular duct. And you can see that accommodating that 1/2-inch tube is much easier than trying to accommodate, especially if you're trying to get all this delivery system out of sight. Here's just another example, a little bit larger tube over here, 3/4-inch tube carrying chilled water would be equivalent to this 12x20 rectangular duct or an 18-inch diameter duct. We are going to talk a little bit more about this concept of distribution efficiency in the next slide. And we're also going to talk about different sources of chilled water. Heat pumps are definitely going to be the more common source, but there are other situations that might be a potential source of chilled water for you that don't involve a heat pump. One of the strengths of hydronics has always been zoning. And just like we can do multiple approaches to zoning with hydronic heating, we can do the same thing with cooling, and we'll show you some of those. We don't have to be concerned about coil frosting. There's a photo of that over here. If our refrigerant charge gets a little bit too low, remember, we're going to cool that coil using a fluid rather than a refrigerant. Low refrigerant volume. Obviously today, as refrigerants are going through an evolution primarily driven by their global warming potential, a monoblock heat pump, even a 4 or 5 ton unit, might have 7 or 8 pounds of refrigerant in it compared to higher amounts of refrigerant in ductless mini split systems and greater potential for leakage. And in the case of a monoblock heat pump, like the Advantage system, all that refrigerant is outside. There are possibilities of using rejected heat. In other words, when we do a cooling process, we might want to take the heat that we're extracting from this water. We might be able to use that heat for domestic water heating or preheating. We might be able to use it in some kind of a process industry. And I think one of the big things that's on the horizon that hydronics is ideally suited for is thermal storage, where we're going to have time of use electrical rates, and we'll be able to design hydronic systems that use heat pumps, hydronic heat pumps, that will coordinate with these time of use rates. So we'll be able to avail ourselves of low cost electricity and then draw from thermal storage when the cost of electricity is high. So there's a lot of benefits that come together that point to using water rather than air as our delivery mechanism on cooling. Now, I mentioned this concept of distribution efficiency, and it's a very simple idea. It has nothing to do with the efficiency of the chiller, the heat pump, or any other source device. It is simply how much energy does it take to move the heating effect or the cooling effect through a building. And we come up with a ratio. We look at, in the case of a design load, we look at the BTUs per hour that the distribution system is delivering, whether it's heating or cooling, and we divide that by the wattage going into the operation of the distribution system. Again, it has nothing to do with the source equipment. It is totally focused on the distribution. And we'll do an example here. I just picked a heat pump. It happened to be a water to air heat pump, so it's an air side delivery. It had a nominal 3/4 horsepower motor to deliver about 1,500 CFM. And based on the published specs for that unit, at that flow rate of air, it needs about 690 watts. And it was delivering 53,000 BTUs per hour based on a source entering source water temperature of 60 degrees. And it says compare the distribution efficiency of that distribution system versus an equivalent chilled water system. So under the blower here, you'll see here's the ratio. This is what was being delivered, 53,000 BTUs per hour. 690 watts was required. So we come up with this number over here, roughly 77 BTUs per hour per watt. So, what does this number mean? It means for each watt that has to be supplied to the distribution system, that system is delivering approximately 77 BTUs per hour from wherever that energy is being generated to where it has to go within the building. Now, here's the hydronic equivalent of that. This is a small circulator, and based on the 53,000 BTUs per hour and a wire to water efficiency on that circulator of only 22%. These small wet rotor circulators, especially the what I'll call what soon will be legacy circulators that use permanent split capacitor motors, they aren't all that efficient. So at 22% wire to water efficiency, that means 22% of the electrical power that's actually supplied to the motor is actually being converted into hydraulic power. But be that as it may, we need about 76 watts. And if we, and actually that should be 71.9 right there. If we divide this out, we're getting 737 BTUs per hour being delivered per watt. So it's almost a 10-to-1 ratio here. The water side is delivering the cooling effect, or at least transporting it through the building, using roughly about 10% of the electrical energy that the air side requires. And this has always been the impetus for using chilled water, even in large commercial systems. Today, we see in larger systems chilled beams or radiant panels being used for cooling. And the underlying incentive is to move that transport of energy from air side to water side because of the inherent ability of water to store that heat and transport that heat compared to air. Now, of course, variable refrigerant flow systems are definitely out there today, and they're smaller cousins, so to speak, the ductless mini split systems. And one of the I'll call it quote unquote arguments I've heard for using these is that there is no pump required. A hydronic system, you need to have a pump or a circulator to move that fluid. Well, that's a little bit misleading, because to move that refrigerant through all that tubing, that requires compressor input power. And what this graph is, it's showing you the power required as a percentage of compressor power simply to move energy through the distribution system. So the red line shows you as the distance from the compressor to where this refrigerant has to carry that heating or cooling effect. As that goes up, the amount or the percent of compressor power that's actually going into overcoming the friction of that refrigerant moving through that piping goes up pretty substantially compared to a hydronic system where we're using water. So again, it's a bit misleading to say that a VRF system doesn't require a circulator. It doesn't, but the compressor has to do the moving. So again, hydronics here has got a very decided advantage over refrigerant in terms of power. I put a slide together just to show you. I'm sure many of you have looked at systems like this. How does the choice of cooling system affect the exterior aesthetics of buildings? And we can go anywhere from window shakers to rooftop units. This is actually a system not too far from where I live. I had nothing to do with this system, but whoever put this in decided that they were going to locate the equipment out and put these very large ducts in. This is in a climate that's about 7,000 degree days in the winter. This is another one not too far from where I live. This is a metal roof, and snow slides off that roof and lands right on these units. Over here, we've got a ductless mini split system, and you can see when you get into multi-zone systems, you get a lot of tubing that has to come out the side of these units, and oftentimes it's tucked into these PVC channels and routed along the exterior of the building. Now, the air to water product from Enertech, the Advantage system, it does have an outdoor unit. It's a very aesthetically clean, contemporary look. And there are two pipes on the back of that unit that in this project go back through the wall and go back into the mechanical room. But it is, in my opinion, much neater than what we have here. And I do want to point out, if it is a geothermal water to water, there's nothing visible. Once that is installed outside, there's no exterior visible equipment. So aesthetics, both with air to water as well as geothermal water to water, are improved compared to this. If you're new to cooling, if you're thinking about getting involved with hydronic cooling, you definitely need a way to do cooling load estimating. And that would be a whole webinar or course in itself. But I'm going to summarize that when we look at a cooling load, we break it up into two sub-loads, what's called sensible cooling and latent cooling. Sensible cooling has to do with temperature change. Heat gain to building can be heat conduction through the building's thermal envelope, the walls, the doors, the windows, and so forth. It could be sunlight coming in through those windows. It could be heat generated from lighting or interior equipment, or a portion of the heat, the metabolic heat output of any occupants. A portion of that output is sensible heat. Latent heat has to do with moisture. Anything that adds moisture to the interior air is considered latent. So it's moisture carried in by ventilation air. It could be air leakage due to infiltration, just like we have infiltration in heating mode. We have infiltration in the summer. Obviously, we cook, we take showers, we wash floors. Anything like that does generate moisture inside the building. And ultimately, to control relative humidity, that cooling system has to remove that moisture. So we need to do separate or segmented calculations dealing with both sensible cooling load as well as latent cooling load. And there are many ways to do it. Probably one of the best recognized methods right now is Manual J from the Air Conditioning Contractors Association. In the old days, that was a manual spreadsheet. These days, there are a number of companies that put out Manual J certified software. WrightSoft is one common one. There's another one called CoolCalc. So from a practical standpoint, if you're going to get involved with doing cooling, you do need to have a tool, a method to do this cooling load estimating. And with that, I'm going to throw this back to Jeremy, and we're going to take a couple questions.
Thanks, John. I will go ahead and pass this first one along to you. But where do these work best? Retrofit applications versus new homes?
And this is in the context of air to water, I assume. So they can work in both. They can actually work very well in new construction. Key concept applying any hydronic heat pump in new construction, design the lowest water temperature distribution system you can. radiant floors, panel radiators, fan coils, any of that. Keep that design load water temperature below 120, and you're going to be in really good shape. You're going to have very good performance. From a retrofit standpoint, often the air to water is going to be combined with an existing boiler, and there definitely are benefits to doing that. And I know sometimes the question comes up, but a heat pump can't produce the water temperatures as high as a boiler. A key concept there is to use outdoor reset control. Even baseboard systems that might need 170, 180 degree water at design load conditions oftentimes can operate 110, 120 degree water under partial load conditions. So to summarize, I would say new construction as well as retrofit are both good markets for air to water.
Okay, thank you, John.
Mhm.
Got one more here. I'll pass this one over to Justin. How do you market this approach when the go-to ways are conventional thinking?
Yeah, if you're going to get involved with an air to water heat pump and trying to implement this into a home with conventional delivery systems, I think, as John kind of alluded to, and how efficient hydronics is over for delivering BTUs. Here at Intertech, we've done some really interesting things like getting rid of buffer tanks, which I know is a departure from conventional install methods. Uh, you know, these systems allow themselves to be incredibly flexible when you're doing hydronic heating and cooling. And so you can really do some interesting things, but there are some new techniques and install methods and stuff that would certainly, kind of increase your toolbox, if you will, for contractors and stuff that might be watching this.
Okay, thank you, Justin. And with that, I'll turn it back over to you, John.
Okay. Well, let's talk about chill water sources. Where can we get water that's suitable for hydronic cooling? Well, we're going to, as I mentioned earlier, we're going to focus primarily around air to water heat pumps. And, a very simple concept here using a monoblock air to water heat pump. We have fluid coming in. It's typically a mixture of water and antifreeze. And we've got a diverter valve. And one position of that diverter valve would send heated fluid down through some type of, preferably a low temperature distribution system, radiant panel heating or other. If the diverter valve is electrically pushed to the other position, the chill water would be routed up through the coil of an air handler, and a ducted system would deliver that. So it's a very simplified schematic that we're looking at, but that is one source of chill water. Now, something that is very different from that would be lake water cooling. And we actually had an opportunity to design one of these systems a few years ago up in the Adirondack region of New York State. The first thing I want to tell anybody considering this is check with your local Department of Environmental Conservation or whatever that agency is called in your state. Make sure that you can do this. There could be restrictions on anything to do with adding or removing heat or cooling effect to a lake. What it does basically is it brings lake water in. There is an automatic filter making sure that we aren't sending sediment. If first of all, we don't want our pickup line to be laying on the bottom of that lake. We want it up. But with storms and so forth, the water can get turbid, and this automatic filter would remove that. And you'll see we have an isolating heat exchanger here. So the lake water only comes through one side of that heat exchanger, goes back out, gets re-injected into the lake. The other side of that heat exchanger, in effect, becomes our chiller. It's our source of clean, chilled water. It's part of a closed loop system. We have a circulator, and in this case, it just shows it going off to a couple zoned air handlers with zone valves. So again, that is a possibility, and obviously most lakes are, millions, if not billions of gallons of water, and oftentimes near the bottom, that water is pretty close to 40 degrees, especially in northern climates. So if environmental regulations are such that you can access it, and it becomes practical to do this, simply getting the piping in and so forth, that is a possibility. Another possibility, back to heat pumps again, is a water-to-water heat pump connected to some kind of typically a geothermal earth loop. It's going to be chilling the fluid. Again, this will typically be a mixture of water and antifreeze. The circulator is going to send that up through a coil and an air handler, and ultimately it's a forced air delivery system. And then the heat is ultimately going to get dissipated into that earth loop. So water to water. Now here's another variation on the lake cooling. This is what's called a lake plate heat exchanger. It's a stainless steel heat exchanger. Typically there are multiple plates that are put together. And this is submerged in a lake, and it's supported above the bottom of the lake. And this is an entire closed loop system. There is no lake water being pumped up into the balance of the system. We are separating the fluid that's coming out of that lake plate heat exchanger with a hydraulic separator, so we could have different flow rates. And essentially, we have the same kind of distribution system here. So again, before looking at this, the place to start is with your local regulations in terms of what can I put into a lake. Oftentimes, if it's navigable waters, there's going to be restrictions. I know that is definitely the case in New York State, and it may be the case in other locations. Now, how does a heat pump, an air-to-water heat pump perform? Well, this is right out of the installation manual for the Enertech Advantage system. We've got heating data, and then over here we've got cooling data. And these basically give you a snapshot of steady state performance. These are outside air temperatures from roughly 60 all the way up to a very sultry 110 degrees. Here we're looking at leaving load temperatures. This would be the temperature of the fluid leaving the heat pump that would be going off to our cooling distribution system. And you see three different conditions here. And then this is just the capacity, the cooling capacity in thousands of BTUs per hour. This is a graph showing some of that. And you can see as the outdoor temperature goes up, our cooling capacity goes down. This is not just a characteristic of a air to water. This would also be a characteristic of air to air heat pumps. Anytime our condenser temperatures have to go up, our capacity goes down. You can also see that as we go to what I'll call warmer chilled water, the blue line here would be chilled water leaving at 45 degrees. The red line would be chilled water leaving the heat pump at 64. The warmer our chilled water can be and still provide the proper sensible and latent cooling, the more capacity we have, and also the higher the energy efficiency ratio, the higher the efficiency of the cooling process. Again, the compressor speed in that Advantage unit is controlled electronically. If necessary, you can see it can actually hold a 45-degree temperature all the way up through perhaps 108 degrees outdoor air temperature. The capacity will go down, and so will the energy efficiency ratio, but it's still maintaining that chill water temperature by modulating the speed of the compressor. Now, one of the biggest things for people getting involved with chill water cooling for the first time, and it might seem like a trivial point or a no-brainer, but it is critically important, and quite honestly, in my opinion, it's one of the things that I think has the potential to be more problem-laden than other aspects of doing chill water cooling, and that is avoiding condensation on chilled water piping. Okay, so I'll start with this. Some of you seasoned folks may recognize what this thing is. I don't know if these are still being produced anymore or not. If you've never seen anything like this, it's two thermometers that are mounted on a frame. There's a handle over there on the right side, and one of those thermometers has this little cotton wick on it, and that gets dipped in water, and then a person picks it up by the handle and literally spins it around in the air. It's called a sling psychrometer. I have to say that very slowly, sling psychrometer. And what you do with this is you get a wet bulb and a dry bulb temperature. If you've ever wondered where that term wet bulb came from, this is where it came from. The thermometer with that wick on it is what gives you the wet bulb temperature. The one without the wick gives you the dry bulb temperature, and then you go to a psychometric chart and you can figure out humidity. Now, I put together another graph that's a little easier to work with. If you know the dry bulb temperature of the air just with a thermometer, and you have a reading for the relative humidity. If you know the relative humidity and dry bulb temperature, you can calculate or look up on this graph what the dew point temperature is. Now, the dew point temperature is the temperature of anything that will cause the moisture, the vapor in the air to begin to condense. So in the case of 50% relative humidity and a dry bulb temperature of 75 degrees, the dew point is right around 55 degrees. So anything that goes below 55 degrees, be it the outside of a glass of, whatever, soda, be it a circulator, be it a pipe, anything that gets down to 55 or below 55 is going to have condensation, and it can get ugly. And I wanted to show you it's a real issue. Here's a circulator volute. Now this circulator is still operating fine, but if you take a look at that volute or the volute on this circulator or that circulator, and I'll be the first to tell you this, it doesn't depend on the brand of circulator. This will form on just about any brand of circulator. What's happening here is that cast iron volute, it's not insulated. If it's running with 45 or 50 degree water, it's typically below the dew point, especially on days with high humidity. And the corrosion you see here is the result of that moisture reacting with the iron in that volute. It's a little harder to see it here, but here's an air separator, and here's some plastic pipe. If you look closely there, you'll see there's condensation all over that. So this, you can't cheat nature in this regard. You have to make sure you do a good job with insulation. There's a variety of products out there. Typically in small scale applications, the elastomeric foam products are probably the most commonly used. You can use fiberglass. You can use, there's actual glass-based, cellular glass-based insulation. But typically you don't see that in small scale applications. I tend to like the pre-insulated PEX. This is available from at least 2 different suppliers. You can buy this in pipe sizes all the way up to 2-inch. And it comes just as you see it here, pre-insulated. So here's a photo that actually shows some of that installed. It's being hung on some of these nylon straps. The nice thing about this is you don't have to slide the insulation on. You don't have to glue it together. And you can simply run it as you would run other flexible piping through the building. As I say, there are multiple suppliers of pre-insulated PEX. And in some markets, I'm not sure if this is available right now in North America, but pre-insulated PEX, aluminum PEX tubing. So there are products out there to do it. When you're working with this elastomeric foam, it is critically important that the joints are glued together and the seams are sealed. The concept is not to let surrounding air get to anything inside of this insulation shell, be it pipes or valve bodies or circulators and so forth. Again, just showing you some examples. Here's a brazed plate heat exchanger, a large one. You can see this has been wrapped up with a sheet product. This again is elastomeric foam. Just showing some details down here for nice, neat looking work. I'd like to see 45-degree miters cut, and then these would be glued together. And quite honestly, one of the best tools for doing this is an electric kitchen knife. And yes, I did replace my wife's electric kitchen knife after I stole it for an insulation job. So it works very well to cut this foam, and then the adhesive is a rubber-based contact adhesive. You put it together, it looks good, and you're getting a nice tight fit. I'll show you another product I like. This is a product from the Holright Corporation. These are, they're polymer, but this is a way to mechanically support a pipe. This is actually 1.25 inch copper pipe here. And you can see it goes through here, and there are little fins that mechanically support the weight of that pipe, but the insulation actually can slide inside of this fixture. And you can seal this joint up here with some silicone. So you get basically a moisture tight or vapor tight seal on that insulation, but you also get proper mechanical support so that you're not trying to support the weight of the pipe and the fluid within it on the insulation. If you've done that with stirrup hangers or other types of hangers, you'll see of course, that insulation will sag wherever that mechanical support is. Now, when it comes to zone valves or circulators, it's important. You do want to insulate the valve body. You can see here's a couple zone valves that have got elastomeric foam wrapped on it. And quite honestly, I would love to see more circulator manufacturers offer these insulation shells. These are preformed shells. They are available for some, primarily in the commercial size circulators, but I know Grundfos for one has these in residential size circulators. You want to join this up with the elastomeric foam, and you want to seal all these joints. But I want you to take note, this insulation does not go over the motor can, especially if this circulator is also going to operate in heating mode, because that motor can has to dissipate heat, and obviously surrounding it with insulation is going to inhibit that. There's a chart that you can see. By the way, there is a PDF file of these slides, so if I'm going through some of this data and you didn't quite catch everything, the PDF will have this, but this gives you minimum wall thicknesses based on dry bulb temperature and relative humidity. This would be a typical condition in most cases here. We're looking at the wall thickness of the elastomeric foam, and this would be two different columns. If we're dealing with 35-degree fluid, that it's possible, but that's actually quite a bit lower than necessary for space cooling. 50 degrees would be more typical. And what I found over the years is that half-inch wall thickness works well in just about any residential application. Now, if you're in Costa Rica on the most humid day of the year, when you're up to a 90-degree dry bulb and 80% relative humidity, you've got an extreme condition. You will need to go to a thicker wall, in this case, 3/4 inch or 1 inch. So this is a guideline for wall thickness on insulation to prevent that condensation. And back to Jeremy for some more Q&A.
Thanks, John. I'll pass this first one over to you. What cooling leaving water temperatures for air-to-water heat pumps is typical for radiant systems that need to avoid condensation? What leaving water temp is most common for fan coils as well?
Yeah. The answer I can give you, if you're trying to do radiant cooling, you have to keep the chill water temperature that actually makes it to the panel at least 3 degrees Fahrenheit above the current dew point of that space. The challenge is the dew point is going to change. It's going to change during the day within any given space, and different spaces within the same building can have different dew points. For example, an entry vestibule where people are coming through and letting in moisture, on a humid day, that's going to have a different dew point than perhaps an interior area. A cooking area, an area where there's any kind of moisture generation, is going to have a higher dew point temperature. Honestly, I would tell you, if you're new to small scale chill water cooling, don't make a radiant project your first project. Work with an air handler. We're going to show you some schematics for that. But there is no one temperature. I can't say, it's got to be 60 degrees or 55 or 70. It's got to be at least 3 degrees above dew point. In the case of a coil, traditionally, the chill water supply temperature at design has been about 45 degrees Fahrenheit. That being said, 50 to 55 degrees can work. You can work with deeper coils with more tube passes and actually get both the latent and the sensible cooling effect that you're looking at with 50, 55 degree chill water temperatures. The benefit of going to those slightly warmer temperatures, you're going to get better performance out of the heat pump. You're going to get higher cooling capacity as well as higher energy efficiency ratio.
Okay, thank you, John. With that, I'll pass it back along to Kevin to run a quick poll.
Yeah, guys, we're going to do a quick poll like Jeremy said. If we can take 30 seconds or so, we'd appreciate your feedback. The poll is regarding small-scale chilled water cooling. Either A, have no plans using them, B, expect to install such a system in the near future, or C, already have experience designing and or installing these. Looks like most of you do have some experience or plan to in the near future. So that's awesome. John, I hand it back to you.
Let's run quickly through air handlers. As I mentioned, I would recommend, if you're new to chill water cooling, want to get involved with it, start with an air handler. Air handlers come in a wide variety of geometries. Typically, you can find air handlers in a horizontal orientation. That oftentimes air handlers like this are tucked into plenum spaces in commercial projects, or you can get vertical air handlers. You can also get air handlers, and this is a product that we used it's a GeoComfort product. We used this actually in a house about 4 years ago. This is reconfigurable. It could be either horizontal, as it's shown here, or vertical. You can see it's got return air, it's got a filter. Here's the two pre-insulated, these were 3/4 inch PEX lines, pre-insulated. We're going to talk a lot about this drip pan in just a minute here. Here's the insulated supply. This is all behind a panel up in a finished attic area. Here's another install with a small vertically oriented air handler. We have return air coming down. It's going through a filter bay. It's going through a nice deep coil. In this case, there's a circulator, an external circulator, drives the chilled fluid through that coil. And then here's our supply. And you can see the piping has all been insulated. When this photo was taken, this had not been insulated yet. But this is a good example of where you don't stop with the insulation. This has got to be wrapped up with some foam tape, pieced together with some of the flat stock material. Again, the idea is we don't want any air to come in contact with any of this material. You can leave the handle exposed, but the valve body itself and the volute should definitely be insulated. Now, over here, I've got a cross section. Air handlers that are used for cooling have to have drip pans in them. There are air handlers on the market that are intended for heating only applications. Remember that the coil in the air handler, as it operates, is going to have water condensing and dripping away from it, and significant amounts of water. In some cases, it could be multiple gallons of water in a day, even in a residential application. So the drip pan internal to the air handler is designed to capture that, and then there's a drain that comes out. We want to have a trap in here, and then we have to have a condensate drainage line to carry that either outside the building or where codes allow, tie it into the drainage, waste, and ventilation system of the building. I'm a big fan of a secondary drain pan. This is in a sense the backup to the drain pan that's inside the air handler. You can see it here. It's a molded plastic pan. It has its own drain pipe. And then right here you can see the trap. That trap is in there so that the negative air pressure generated by the blower doesn't pull that condensate back. Or if this was connected to some type of a sanitary drainage system, you certainly don't want to draw any kind of sewer gases back into that air handler. Typically, these traps are supplied with a small brush. You should be cleaning them out once a year because you are going to get a little bit of mold. It's just a characteristic of any system where there's condensate forming. And you want to make sure that the trap is free for flow. Some of these also have what's called an emergency shutoff switch. If that trap does get blocked and the water level rises, that switch will actually be interwired to the air handler, and it won't allow the blower to operate. And the reason for that is if the blower is operating, you're going to continue to form condensate, and eventually that would leak out of that air handler at some position. That's where that secondary drain pan comes in. It actually would capture and drain away safely any moisture that might make it outside that air handler. That's especially important if that air handler is installed over finished space. If it's in a basement, arguably you might want to omit the secondary drain pan. But in this particular project, this is a drywall ceiling under where that air handler is. So we don't want stains on that ceiling. Now, again, you can look at this in more detail in the PDF, but just like circulators have pump curves, blowers in air handlers are rated based on static pressure that they generate versus airflow rate. Okay, and oftentimes today you buy an air handler that has multiple speed tappings on the motor, and it's just like having multiple speeds on a circulator. You get different relationship between static pressure and CFM. Typically, you're going to calculate the CFM you need, and then you're going to design and size the ducting for a certain amount of static head loss. And you want to make sure that the static pressure of the duct operating at the CFM that is necessary is within the capabilities of that blower. Okay. Here's just a close-up view that shows one of the commercially available condensate traps. You see there's little caps that you can pop up. Here's the brush that comes with it. This is just the same view we just looked at here. Again, once a year, make sure you change the filter and clean the condensate trap out on an annual basis. Performance data for these air handlers. Again, this is for one of the Enertech air handlers. You've got several parameters here. The model of the air handler, the entering water temperature from 42 up to 50. Here's the air temperature, 73 degrees with 63%, or I'm sorry, 63 degrees wet bulb. The flow rate that you're pushing through the coil, as well as the pressure drop. So this is all the data that you would use to do the hydraulic calculations on the air handler to make sure that that circuit is getting the flow rate that you want. Here are 4 different speed tappings on a motor, the resulting CFMs that they would produce. And then finally over here, we have total cooling capacity in BTUs per hour and sensible cooling capacity. Latent cooling capacity would be the sensible subtracted away from the total. So this gives you data that allows you to get both the thermal and the hydraulic sizing of that air handler matched to what that cooling load requirement is. Multi-zone, here's some more options for delivering chilled water. Now these are all fan coils. These all have a coil that the chilled fluid would go through. They all have a drip pan in them. There's just different sizes and different shapes. Wall-mounted consoles. Here's a recessed console. Here's one that looks as if it's a ductless mini split, and other than the fact that it has a water coil rather than a refrigerant coil, it is identical to a head for a ductless mini split. It's turned on and off by a remote control. It's got louvers down at the bottom. You'll see they're closed now, but these louvers would open up and they oscillate up and down, just like many of the ductless mini split systems. So these are all options and they can be combined. You don't necessarily have to use just one type in a given building. But I want you to think about when you get into multi-zone cooling, it's important to understand that each one of those terminal units, each one of those fan coils has to have insulated supply and return piping. It has to have a condensate drain. It has to have electrical wiring to it to coordinate operation with circulators and zone valves. It's all possible, but this is quite a bit of infrastructure. And I would always ask the question, if a client says, I want to do 4 zones of cooling, ask them how they plan to use that. Remember that leaving doors open, if you're trying to keep one room at 70 and another room at 80 and the doors are open, it's not going to be very effective. So in my line of thinking, you really need good justification in an average house. Think 2,000 to maybe 3,000 square feet. You need pretty good justification to go to multi-zone cooling. Now, if you're building a 15 or 20,000 square foot, you're building a system for a 15 to 20,000 square foot house, yes, you're going to have multiple zones. You're probably going to have multiple air handlers. But in an average construction 2,000, 3,000 square foot house, my preference is to do single zone cooling and along with multi-zone heating. Remember, if it's a terminal unit like one of these wall units, this just shows cleaning. If you look into that, there's actually a company called WeCleanHeatPumps.com, and they charge $600 to clean a 5-head system on an annual basis. They basically put this plastic diaper, if you will, around the unit, and they use a small pressure washer to clean that coil off. And that is being done in living space. It's not necessarily being done in a mechanical room in a basement. And if you're dealing with single speed heat pumps, fixed speed heat pumps, and you're doing multiple zones of cooling, you're going to need a buffer tank. So again, with a fixed speed heat pump, putting out maybe 3.5 or 4 tons of cooling, and one of these small air handlers only needs, let's say, 3/4 of 1 ton of cooling, you don't want to short cycle the heat pump, so a chill water buffer tank is going to be necessary when it's a fixed speed heat pump. Now, this is the Enertech approach here. If you're not familiar with it, here's the outdoor unit. This is a monoblock unit. And it comes with an indoor unit. Now, the indoor unit in this Enertech Advantage system has pre-engineered and pre-assembled many of the components that you would otherwise have to specify, size, purchase, and install in the field. So they're putting, in a sense, much of the mechanical room is already put together for you. You're going to run 2 pipes to the outdoor unit. This is the domestic water tank. This is a reverse indirect tank. And you can see there's 2 pipes here. I've grayed them out because they're not operating in cooling mode right now. And then finally, we have an outlet here. I'm showing a diverting valve that in heating mode would go over, in this case, to some kind of radiant panel heating. But in cooling mode, it would go over to that zone distribution system. The nice thing about this, there's no buffer tank required. Okay, the compressor speed in that outdoor unit will automatically adjust as necessary to hold a specified leaving chilled water temperature. So as these units turn on and off, that compressor speed will automatically adjust for that. Very different from the case of a fixed speed heat pump and multi-zone distribution. A single circulator that is supplied with that unit is all that's necessary in the system, because the valving inside that system will direct that flow either to space heating or cooling, or direct the flow to the reverse indirect. So basically, most of the installation of this is just piping. Now, here I've taken the same schematic, I've just added some multi-zones of heating. So if we want to do multi-zone heating, multi-zone cooling, yes, we can do it. We can do it without a buffer tank. It's all being driven by the internal circulator in the indoor unit. And it's just a diverting valve that is determining whether that output flow goes to the cooling load or to the heating load. I wanted to throw this in just to shake it up a little bit. This is a company up in Canada. They do zone cooling using a single centralized coil in this sheet metal cabinet. You can see the coil in there, but there's no blower. What they do is they come off with flex duct, and these flex ducts go out to different zones in the building, and within each one of these outputs, there's a small axial fan, very high efficiency fan. So this fan is turned on and off by a zone thermostat, and that thermostat also coordinates the chill water flow through this coil. So they're doing zoning on the air side of the system versus the water side of the system. I wanted to show it to you simply to show you that there are a variety of methods that you can approach small scale chill water cooling. And we've got one last Q&A here, so I'm going to go back to Jeremy.
Thank you, John. Justin, I'll pass this one over to you. What are some options for dealing with smaller zones that will not meet the 3 GPM minimum flow rate without the use of a buffer tank?
So with our air to water system, the 3 GPM minimum flow rate is actually the flow rate between our indoor and outdoor module. We achieve this internally, and so our pump will modulate its speed accordingly to ensure that it always has 3 GPM. Now, depending on the size of a zone, you might only have, 0.8 or 1.2 or 2.4 GPM actually flowing through that zone. Mechanically speaking, we have what's called a pressure differential bypass that is mounted inside our indoor module, which allows this to be possible. It's kind of the key to us being able to do small zones like this without the use of a buffer tank.
Okay, thank you, Justin. And
Yes,
with
sir.
that, I believe we've got one more poll to run, and I'll pass it back over to Kevin.
Yes, we got one more poll. Again, we appreciate you guys' responses on these. Go ahead and launch that. What type of chiller are you most likely to use for a small-scale chilled water cooling system? A geothermal water-to-water heat pump, an air-to-water heat pump, some other source of chilled water, or you do not plan on using this type of cooling? Looks like 61% currently with an air-to-water heat pump. Okay, thank you guys. John, back to you.
Yeah, real quickly, I want to show a few last slides. This is just an example of what's possible on the heating side, where we're using, in this case, panel radiators and combined with a couple radiant floor circuits. These panel radiators are all operating off of thermostatic radiator valves. So we're doing pretty extensive zoning on the heating side. And of course, there are other options. We could use zone valves and so forth. So we can zone the heating side, but then go back to single zone for cooling using either an air, vertical air handler or horizontal air handler. And these are just some of the advantages of doing that. You're going to save quite a bit in terms of installation costs on the cooling side by going with a single air handler. Certainly the wiring is less. You're consolidating all the condensate at one location. I like that idea because now I have one location where I can go clean that trap out. I can service it, and there's really only one location where any condensate is being generated and has to be dealt with. And there's only one coil that has to be periodically cleaned, and also a filter that needs to be serviced. In some cases, in both these cases, these air handlers are completely out of sight. So when aesthetics are a high priority, we don't necessarily want to have high wall units or console units available. Okay, this is just an example. Again, you can look at this in the PDF. This is a generic schematic, just using a generic air-to-water heat pump. The thing I want to point out here is this tank is doing two things. It is acting as a reverse indirect water heater, and it's also acting as a buffer for this zoning. Now, again, this is different from the Enertech Advantage system. Let's assume this is just an on-off air-to-water heat pump, and we have all this zoning going on out here. We're going to need some kind of buffering. And the other thing you'll see, there's a diverting valve. Here's the cooling coil in the air handler. And this actually has a heat recovery ventilator tied in with it as well. This is actually a system that was built a couple of years ago in upstate New York. It works well. This entire distribution system is powered by one circulator that draws at full speed 44 watts of input power. So it has a really high distribution efficiency. The last point I want to make, there's a lot of components here that would have to be individually specified, purchased, and assembled on site. And as you're going to see, the Enertech approach is to take much of this and put it together into a compartment that is going to speed up your installation. Just another example of a similar system. Here, we're not heating the water all the way up to the full domestic water temperature. We're using this tank as a preheat, and then we're going to do a final heat through something else, be it a tank or an electric heater. In this case, we're showing an external electric boiler. And again, the takeaway, I just want to show you there's a lot of components here, valves, circulators, heating elements, check valves, and so forth, that can be purchased and installed in the field. But I want to compare that now to, again, Enertech's approach. Many of those components are already consolidated into this cabinet. So the thing I like about this is we know the engineering was done correctly, we know the assembly was done correctly, and it's going to save a lot of time in the field. Essentially, this is going to be mounted on the wall, and the majority of the work is going to be running piping between the outdoor units, the indirect water heater, and if you are doing cooling with a coil and you're doing something separate from that for heating, there is going to be some valving requirement external to this. But in a very simple system, if you were just going out to say just an air handler, this valve wouldn't be necessary. So again, you can see a lot of components all built together. The other thing, one circulator is driving this entire system. And as Justin pointed out, that's a variable speed circulator that will adjust along with the compressor speed. Here's a detail. This is the same system. What I've done here is I've drawn a small amount of heating off of the side of that tank. Now, that is a Turbomax brand tank, and Turbomax is supplying these tanks with extra side connections. So let's say we put this system in, and 2 years from now, we want to do a towel warmer in the master bathroom, and we want to put a couple panel radiators in the basement. Rather than tie in over here, we could simply pull that off of the side of that tank, because that tank is going to be maintained for domestic water heating purposes. It might be 125, 130 degrees, depending on the settings on the indoor unit. So we can take a small amount of heating off of that tank, and this would be, again, a variable speed pump, very low power requirement, and these individual heat emitters over here are just controlled based on thermostatic radiator valves. So it's a nice little add-on detail that you could do initially or down the road. This is a feature that you can sell as an expansion of the basic system. Here's the same system where a boiler's been added. You'll see the boiler is actually added to the piping coming in from the outdoor unit. The latest version of the Enertech Advantage system has a 0 to 10 output that can modulate this boiler as necessary. Assuming this is a modulating boiler, that 0 to 10 volt signal can set the output of that boiler just as necessary to get the proper supply temperature to, in this case, it would be the heating load or the domestic hot water tank. And that's a nice, unique feature. And again, a very simple tie-in for that boiler. And finally, I'll wrap up with this. This is a project that Justin and I both worked on. It's near Albany, New York. This is one of the first installs of the Enertech Advantage system. Here's the outdoor unit up on a snow stand. Here's the indoor unit. You can see it mounted on the wall. Here's that air handler we looked at earlier. Here's the TurboMax tank for domestic hot water. And if you look really closely up here, this is that expansion manifold. This is for adding that towel warmer, those panel radiators in the future, and there's a small circulator for that. Right now, there is nothing connected to that, but again, that is a nice feature that allows you to expand the system in the future. Here's a glycol feeder that would put fluid back into the system as air is vented out, ensure that system stays up at pressure. So that was a nice, neat looking installation. If you want to see this actually during some of the installation, just go to this address on YouTube. This was featured along with Ross Trethewey, season 20, episode 13 of This Old House. And with that, we're going to land back on Q&A, and I'll turn it back over to Jeremy.
Thank you, John. I believe we're going to do one more question here. Justin, I'll pass this one along over to you. Is there any value in providing a gas backup source of heat when using an air-to-water approach?
Yeah, absolutely. As John kind of mentioned briefly, that we have the ability to modulate an external boiler. I think it opens up a lot of interesting possibilities and allows you to cover a really wide swath of applications when using a dual fuel based system. The heat pump can take over, 80-90% of the heating and cooling duties for the home. And in those handful of days every year that get cold enough, if you're in that sort of climate, I think it's a really good answer to be able to back the system up with the boiler. It also allows us to do things like run much smaller electrical requirements in power outage situations if we're going to run off of a generator or something like that to power a boiler. And with our indoor module, we use the backup boiler to back up domestic hot water and space heating. So it offers a lot of flexibility there.
Yep, and with looking down the road too, with off-peak rates, potentially operating that heat pump on off-peak, low-cost electricity, and to avoid a very high-cost peak, you may choose to switch over to the boiler. That's just another option that could potentially fit there. Okay, so I'm going to turn this over to Justin. He's going to talk about the next webinar.
Thanks a lot, John. So on the next webinar that we have coming up on November 14th, we are going to talk a lot about new heat pump technology. So we have a lot of exciting new features coming out on our Advantage air to water system. I'll also talk a little bit about some new updates as it applies to our variable speed water to water product, and things like adding in a dual fuel capability, modulating boilers, cascading heat pumps, and connected controls. We have a lot of new exciting updates to discuss and talk about, and we're going to get kind of deep into those subjects. So if you're interested in learning some new stuff and what's going on behind the scenes at Enertech, make sure you come back and join us. I'd appreciate it if you guys would share this out to other people within the industry. And, we would like to expose as many people to this type of technology as possible. I think there's a lot of advantages with a system like this, certainly a tremendous amount of flexibility. And with energy costs going up constantly, there's a lot of really, really good solutions here. John did a fantastic job talking about small scale chilled water applications, but there's a lot more that we could talk about on this subject. You got anything else you want to add, John?
Well, just here's the contact information for Enertech websites here. I'd encourage you to take a look at their website. I just want to reinforce something that Tim mentioned. To my knowledge, Enertech is the only company that is building an air-to-water heat pump in the U.S. And
That is
I've had a
correct.
chance to see their production line. It's state of the art, and the product itself very much a state of the art product.
Yep. Yeah, most of the air to water heat pumps on the market right now are being imported. A lot are coming from a few different places in Asia and a handful coming from Europe. And yeah, right at the moment, we are the only US based manufacturer of air to water.
Okay, guys. I hope this was super valuable for everyone that joined the call. And we hope that you can join us on our next month's webinar that Justin laid out for us. In our post-webinar email, as we mentioned, there will be a link to register along with a recording and PDF of these slides from today's presentation, and then also a invite to join our Facebook group. Don't forget, like Justin also said, share this registration link with your family, friends, and colleagues. We would really appreciate it. And from Tim, Justin, John, Jeremy, and I, we thank you guys for joining. Hope to
Thank
see you
you
next
all.
month.
Thanks a
Thank
lot.
you all.
Have a good one.